So our last talk comes from Alistair Stewart, who is a researcher at Web3 Foundation, and he's going to talk about slashing in sharded systems.
So I want to talk about slashing in proof-of-stake systems, in particularly ones which are sharded. I think it's still kind of a surprisingly open question about whether slashing is a good idea in the first place. So I sort of want to address that as well. And of course, I want to talk a bit about the system that I'm working on, Polkadot, and how this applies to that. So sort of the basics. We like to argue in permissionless blockchains that they're secure if enough participants or enough power is rational. And the sort of way you'd want to do that is you'd want to reward consensus participants for helping secure consensus. And in a proof of stake system, basically you want to make the power that's sort of consensus constitutions sort of proportional to the amount of stake backing them. And then you want to argue in the end that if most stake is in the hands of rational and ideally active people, then the system is secure. And one of the things about proof of stake protocols, which sort of differs from proof of work and other, or just proof of authority, is that we can punish participants in a different way. Because they have stake, we can take it away. So as well as rewarding them, we can punish them. And often by a lot more than we're actually rewarding them. Now, I say we want to argue that under rationality assumptions that these protocols work, but actually we can't sort of prove that they work under this sort of pure sort of assumption. And there's a whole load of different types of assumptions we could have made. So typically what we'll do is that we'll prove that they're going to work under some honesty assumption, sort of a majority of participants, a majority of stake is honest. And then we'd use other assumptions that go beyond honesty to analyze possible attacks, because this we can do. And hopefully we want to argue at the end that honesty is actually rational. And so one of the questions about is slashing a good idea? Often this sort of boils down to is to whether we can get more by making economic assumptions as well as honesty assumptions. Now, as I say, there's an argument that maybe even slashing isn't a good idea at all. And for a single chain system, it sort of looks like this. So we have a Byzantine fault-tolerant protocol. It's secure if bigger than 2/3, or maybe bigger than half. It sort of depends on what you assume about the synchrony of the network. If a certain fraction of consensus participants is honest, then it's secure. And what's more, you can sort of design these such that actually the performance penalty of people who are dishonest isn't that big. So it's like if we have bigger than half or bigger than 2/3 honest people, who cares? About dishonest people, we don't really need to punish them. And on the other hand, if we actually have majority dishonest or bigger than 2/3 dishonest, and all those people were colluding together, then they can basically agree on any valid thing, and everyone else, if they follow the rules, will accept it. And because of this, if we're in this situation, that they can censor the chain. And they won't include any reports that cause them to be slashed, obviously. So we're not punishing them, even if we have slashing. It's sort of particularly clear in like the half case, because if the majority of people are honest, then the protocol works. We don't care about dishonest people. If bigger than a third of people, if half of people are dishonest and they're colluding, then we can't punish them. And even in the third case, when we only have this factor of 2, if we have between a third and 2/3, then typically we won't be able to agree on anything. And again, we don't punish the people who are attacking the system. So if we can't punish the people who are attacking the system, then what would slashing get us? Well, I mean, when there isn't a successful attack, it does still disincentivize incorrect behavior. But the downside is that it makes it, there's now a bigger security issue to stake in the first place. If now I might be punished, I have to think carefully about my setup and if anyone's going to sort of steal it, if I'm going to go offline, if something bad's going to happen. And this will, and sometimes I'll have to lock my stake too, generally. And so there's some disadvantage to participating in staking if we have slashing. And if we sort of arguing that the more stakers get involved, the more stakers involved, the more our security is against attack, then so then there's an argument to be made that maybe the system is more secure if we don't have slashing. And actually, as a result, like there are systems out there that don't slash. These are typically, oddly enough, the professor coins, the academically originated projects like sort of Algorand, Avalanche, Cardano. And often this is because cultural thing, right? They want to prove their protocol is correct, and they can prove it's correct under honesty assumptions. So you don't really want to sort of hand wave and introduce rewards and punishments too much because you might make mistakes, and if you don't actually say anything about it, then it's sort of harder to reason about. But actually, I think there's almost a good case here for slashing not being a good idea for a single Byzantine fault tolerant system. But one thing I really want to argue is if we have sharding, if we have interoperability, if we sort of have multiple systems, then it becomes more interesting. So, and the main reason for this is basically because if we have sort of misbehavior on one chain, often we can report it to, we can post about it on a different chain. So like layer 2 protocols like Plasma, etc. What you do is you would make most transactions off the chain, but then you'd use the main chain for disputes resolution. And basically, this will get you scaling in principle, if not everything is disputed. And the reason you can do this is because people lock collateral on the main chain and they can be punished. And often we will take this approach too with sharding, when we'll have a central chain, our main chain, sort of relay chain, beacon chain, hub. These are often similar things, concepts that we can sort of report misbehavior to. And it's not just the case in this sort of scaling solution, but also in interoperability solutions. If we can post something to a bridge chain, like so we have one chain following the consensus of another, we can post misbehavior to the original chain where the consensus participants are. And so the sort of the first question is, does this help? So let's sort of consider let's make only on honesty assumption. So we consider a sort of typical sharded system. We have S shards. We distribute our validators, these sort of participants with equal power between them. We'll do this randomly. And sort of every now and again, we'll change the assignments. So every time period, we choose a sort of a random subset of size M, and that'll be the guys for this shard. And then each shard does a Byzantine fault tolerant protocol. And so what we have to do here is we can make this work. If we assume a bigger honesty percentage for the entire system than we need for any shard, like say 2/3 or 5/6 instead of a half or 2/3, then if we have enough validators, with high probability, all of these shards will be majority honest. Okay, I want to get a bit concrete about this. So this is as much as I could get on a slide. So let's sort of suppose that they're independent, the validators are chosen independently. They independently choose whether they're bad or not. This is not quite true because there's a lot of slides, it's almost true. And then we can get a bound using Chernoff bounds. So Herford inequality gives a particularly easy expression here. And what we want sort of, so we have sort of S shards and T time periods, T set validator sets we're going to assign to T times we assign validator sets to these shards, and we want some sort of probability P they know to occur, like say, I have 100 shards. I want to sort of be secure for, suppose I change them once a day. I want to be secure for 40 years. Actually, in Polkadot, we change them 4 times a day. So this is 10 years I want to be secure for. And we sort of have a 1% chance of failure. And we put all these things in. It scales quite nice, logarithmically in all these things, but the constant is not amazing. And it tells me I need 338.4 validators on each shard. Now, this analysis isn't tight, but it's not too far off. And yes, we do need hundreds of validators for each shard. And sort of one of the claims of this talk is that we can do better with economic assumptions. And this is important because it means we can scale better, right? That if we reduce the shards per validator, we can increase the number of shards. So what would we do if we had slashing? So the basic idea is we do what we do in a layer 2 system. The first idea, that is we use our central chain, which is not so scalable, to handle disputes. And this is great because if one validator in a shard is honest, then they can report the misbehavior, which is a lot nicer. You're going to get a lot nicer numbers than we had with 2/3. So what they'd have to do is they'd have to include a proof, if misbehavior, if there is one. If there's not, then maybe, say, for validity, we'd end up having to have everyone check the block, which is very unscalable. But the point is although this isn't scalable, what we can do is we can decide, we can have everyone decide is this correct or not, and then we can slash, either the reporters or everyone who claimed it was honest, everyone who claimed it was correct. And if we always slash someone, then there's a cost to breaking scalability. And because of this, we can sort of limit the amount of times it happens overall. And so we're still overall a scalable system. And so now the numbers are better. In particular, it's sort of 2/3 of the number of people in a shard is the probability that they are all honest. And so this gave me a number with my things of 46.3, which is, a bit better than our 338. But there are sort of downsides with the simple protocol. I mean, the most important one is data availability. If one honest validator doesn't have the data, they have no hope of being able to check the correctness. But this is actually kind of solvable. And sort of Dankrad mentioned, the basic way to do this would be to use erasure coding. So in Polkadot, the way we do this is basically we'd say, let's give a piece of the erasure coding to every validator for every shard. And this isn't too much data. But now we can all agree that something is available. And then in principle, we can reconstruct it. But the other downsides are perhaps more important. So one of them is that the attacker knows when to mount an attack. So basically, the number of validators assigned to a shard is public. So we just wait until they're all colluding with us, and then we launch our attack. And when we do that, how much are we going to get slashed? Well, it was only a one in a number of shards, a number of participants who were on this shard. And if we translate that into stake, if they're sort of equally backed, that means that we have sort of order of one in the number of shards fraction that we slash. And if we sort of imagine this is some sort of security level, then we're not really gaining anything from being in a sharded system versus all these things being independent. The only thing we're really gaining is that we're sort of evening it out. So can we really do much about this? Well, okay, so let's sort of, it doesn't seem that by assigning validators differently, we can get around this at all. So the problem is that, so if checking validity is atomic, and each validator can only check a constant number of blocks, otherwise we'd be breaking our scaling, then the average number of validators to check has to be sort of 1 in S, and this gives us this total state divided by number of shards that we're slashing. At least for the least check shard. Now, both of these assumptions aren't necessarily true. One we can get around by sort of checking the validity of little pieces of the block. I don't think that really helps. More people help do the numbers, but it's still a small amount of stake who's checking each individual thing. For the second, yes, we can. As Dankrad talks at length in his talk, we can do succinct proofs, ZK rollup, but it's not feasible to do that yet, especially not for sort of general computation chains. Yeah, and then this is an issue. And so Brian Ford and Rainer did a rather nice blog post that later became a paper called Rationality is Self-Defeating and Permissionless Systems. And it makes very many nice points, of which I'm just going to select out one and attack it. You should go read it to read all the others. And one of the key arguments was, so some of the nice things that they do are sort of come in the region of the fact that I don't know how to analyze systems from rationality alone. But what this particular argument went something like this. So the total amount of money in the world is bigger than the amount of state, securing the system, which in turn is much bigger than what the actual total reward and punishment for actors capable of attacking the system is. And this certainly was holding true for our sharded system. And then they made the argument that, okay, so why don't we just spend V and attack the system? Now, ideally, we'd be able to steal bigger than V money. We might be able to because the amount of tokens in the system is much more. But at the very least, we can probably just take it down. And then maybe we just need to short the token, attack the system, make more than V money, and we're done. So why do I think this isn't really fatal? So one of the issues was the one I mentioned 2 slides ago. So in this model, the attacker knew when they could get away with an attack. And indeed, if this is the case, then it's only going to cost them 1 in S to attack a chain, or less fraction of taking the system to attack a chain. But if we can imagine what would happen if you weren't certain when you attempt to do an attack that it was going to succeed, then sort of you'd have to pay for every time you unsuccessfully attack the system, as well as for your successful attacks. And so rather simply, you can say that the expected cost of an attack is going to be the cost of the attempt times the sort of ratio of times this actually succeeds versus being detected. So time to detection probability divided by the success probability. So we want to boost this up, then really what we want to do is we want to make sure that, contrary to this circumstance we had before, where these probabilities, the detection and success were equal, we want to make the detection probability much higher. So we want to sort of make attackers sort of commit to an attack and then probably fail. And this means if we do this, we can get the amount of security like up to the number of tokens in the system. To do that, we just do 1 in S, or maybe even higher. Doing M, the total amount of money in the world, it's not unfeasible. But to get 1 in S, and sort of this point, you might argue that it's harder, it's easier. We might as well just buy all the staking tokens and attack the entire, attack the top layer, the Byzantine fault tolerant top layer, rather than just attacking one of these shards. And the big gain here is this probability of 1 in S. It's much bigger than the failure probability of 1 in S times the number of times we would take the validator set before, because in fact this log T term was, T was actually much bigger than S. Our number of rotations was bigger than our number of shards that we might have to consider. And doing this kind of helps a number of validators. So let me sort of look. So how do we going to make this work? How are we going to have the attacker not know? Basically, we want to use participants that are not publicly known. So, if participants are publicly known, they can be attacked. If we can sort of choose them in a way the public doesn't know, and proof of work already does this quite nicely. We don't know which miner, it's random which miner ends up producing the next block. So we can't, so attacking miners is going to be really hard. In proof of stake systems, like Algorand and Ouroboros worked on this for a while, you basically use a verifiable random function. It's an easy way, or you could use public randomness. And then you can get a protocol that works under honesty assumptions, even though there's a few participants deciding what the actual outcome is. Now, there's sort of trade-offs with this, which is you could imagine a world where everyone hack software, they hack their own software, and then other people on another chain, I can offer a bribe, buy a smart contract, and then you can just prove that you're a participant. So effectively, if I'm allowed to bribe everybody, even people who I don't know who are in advance, then you can attack the system. Under honesty assumptions, so this is one of the difficulties of dealing with rationality assumptions, but under honesty assumptions, it works. So what we'd do in Polkadot concretely, so we choose our validator. We'd have some of our validators be assigned from the shard to start with, and they would check the block and tell the main system that this block, which they give by a hash, well, completely is correct. And then we'd sort of try and decide that it was available. We'd distribute some LHU code to pieces to do that. And now we'd have people choose at random to check this shard. And they're going to be able to get hold of the block. They might have to reconstruct it from erasure coding. And then they're going to check its validity and tell us if it's correct. And if any of them say it's invalid, then just like this challenge thing, we escalate. Otherwise, after some period, we're going to agree on it. And what this gets you, if you look at the numbers, so we have 2/3 of validators are honest. They each have got some chance. This number of people we can assign in the second step, chance to be assigned to this shard. It's approximately +1, and we end up with this thing here, with something very similar to what I had 2 slides ago, but a bit worse. But the advantage is there's no T in this logarithm. And so I get here that we only need 13.8 validators to validate to check these shards on average in order to get that it's easier to attack it's harder to attack the shard than it is to attack the central chain, which is sort of the main point I'm going for. Now, I might briefly say I think we can get this sort of idea also works for bridges in a sense, in that we could we want to do this commit to something, then have random number of people, random number of consensus participants say something. And so I think we can apply this to the situation where we sort of have a chain that wants to follow the consensus, or even just a light client, but it can't verify signatures very cheaply, or can't even store signatures very cheaply. And this will be the case at the moment for bridging to Ethereum. If we had fancy crypto, we could do this better, but I think we can do the same ideas for interoperability. And I've been working on that recently, but this still isn't sort of ready. And this is where I'm at. So I wanted to, So I want to sort of argue that it made sense to combine economic and honesty assumptions, and that concretely, I think we can get far better scaling in terms of number of validators. Number of shards we can get for the same number of validators. And I really want to say that consensus systems not being in isolation is really what makes rationality assumptions interesting. I think there's some bad results on this end, but there are probably also some positive results, and I'd like to see more of them. Okay, that was Thank you.
Okay. Yeah. So, what do you mean by combining economic and honesty? You mean that we assume some parts of the system to be honest, Byzantine, and some other parts to be rational, Or
Not really. So we assume that. So in this case, actually, the economics can almost be put as bounding the cost of an attack actually bounds within some time period the number of attacks you can make. So if you make it more expensive than the system, then actually, there's not probability one that they can keep on attacking even if they had like all the tokens at some point. So it does gain you a bit more than that. But yes, what I mean is that we're going to make an honesty assumption about the entire system, and then we're going to try and attack some portion of it and argue that it's going to be expensive.
Nice. That's pretty interesting. So, for example, like you can assume that the main chain has honest Byzantine, it's secure, and then for the smaller parts, you actually do the economic rational argument.
That's exactly what the argument I'm trying to make here, and we're going to try and make for.
I think it's interesting. I actually have some work on different things like layer 2 stuff, where we do a similar thing. We assume the chain works, and then we prove incentives on the channel and how it works. So I think that is a really nice path forward. I want to thank everyone for being here and for presenting. I think that this was a really nice workshop, and we attacked scalability and interoperability from multiple angles. And I welcome Fatma to also give some conclusion.
Yes, I would like to thank everyone, Lefteris, also our organizers in the Foundation, Sonia and Kristen. I would like to thank Moti and Yuka from the DIS conference. It was indeed a very, very interesting workshop. And I would also like to thank the audiences here. We are going to add more information about these talks on the website. All of these talks are recorded, so we'll try to see whether we can add the link to the videos on the website so that later on you can also look down and watch one of the talks if you couldn't follow something or want to look at it again. Thank you, everyone, and have a nice weekend.